In this video, we're going to do the practice examples in your notes on electron configuration of ions. We'll do phosphide and lead ions. But just a quick recap, we saw how to write electron configurations for cations and anions in the previous video. We generally saw if you're nonmetals will gain electrons to become like the noble gas that comes after them. And typically metals will lose electrons to become like the noble gas that comes before them. So generally when the nonmetals gain electrons, they'll be isoelectronic to the noble gas that comes after them. We often say that they have the same electron configuration as a noble gas that comes after them, and that was called a noble gas configuration. They don't become that noble gas because they have different number of protons, but they have the same electron configuration, and that's called a noble gas configuration. So typically metals will have the same noble gas configuration when they lose electrons to become like the one before them. So for example, Na plus would be isoelectronic or have a noble gas configuration of neon, whereas chlorine would have the noble gas configuration of argon. Now, that's a bit simplistic. It doesn't always quite work like that. There are some elements, some metals, for example, especially in this region over here, that will lose electrons to become like a noble gas, but they're not exactly like that noble gas. So for example, if we look here, we had zinc. Zinc lost 2 electrons, but doesn't have the exact same configuration as the noble gas before it. Zinc, the noble gas before it is, let's go take a look. We have zinc over here, argon. And so argon's configuration is more like this with 3s, 3p. But zinc, on the other hand, has this 4s, 3d over here. So what that means is that, actually, let's go back and take a look. Did I correctly select argon? Yes, so zinc wants to be like argon. And again, argon's configuration is more like this as opposed to being like this over here. So there's something a little bit off here. It didn't lose all these electrons to become like argon. It still lost electrons, but it didn't lose all of these electrons here to become like argon. It just lost the 2 in the 4s and left a 3d there because those 3ds are very stable. But this is still a stable arrangement because, again, of that nice 3D full shell there. So even though this is not like argon, what we might sometimes say is that this is called a pseudo noble gas configuration, meaning that it's still stable, but it just doesn't match the noble gas exactly like it should, like we saw, for example, with the sulfide ion. That matched noble gas after it. If you did the configuration for Na+, it would match exactly neon. If you did for K+, it would match exactly argon. But because of those d electrons there, it doesn't match argon exactly, but it's still stable. So we say pseudo noble gas configuration. Pseudo basically means like fake. It's not the exact same configuration as the noble gas for it, but it's still stable. Generally, a pseudo noble gas configuration will happen in those d block elements, in the transition elements, and you'll usually see that in their final configuration for the ion, they'll have 18 valence electrons. So for example, we have 10 over here, 6 over here, and 2 over here. That's a total of 18 valence electrons. Whereas in the actual noble gas configurations, real authentic noble gas configurations, you have 8 valence electrons, 2 and 6 here. That is 8 valence electrons for these real noble gas configurations as opposed to pseudo. There is an extra video in your handout at the bottom of the page over here that you can watch for pseudo electron configuration and electron configuration for some more details and other examples. But that was just some more details on noble gas configurations when ions form. Let's go take a look at phosphide and lead ions and see if we can apply our understanding for coming up with ion configurations. So we'll start with drawing the neutral element for phosphorus. Phosphorus has 15 electrons a place. So let's go ahead and do that, 15 electrons. It is a non-metal, as you can see. It's right over here. there's 5 valence electrons based on the group number, so we can predict it'll probably want to gain some electrons, and it'll probably want to become like argon, which makes sense because in our little table over here, we say it becomes P3-, but it will become like argon. So let's take a look. So we have 15 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So notice that I added those singly first. I didn't pair anything yet. And now I'm going to go ahead and make the electrons. So and add the electrons. So this was phosphorus with 15 electrons. And we can see that we're not going to remove electrons, or rather we're going to add electrons to fill up this highest energy sublevel here. The orbitals need to be filled out. And we can fit 3 more there to become a full valence shell. So for P3-, we're simply adding 3 more electrons to the outer shell. And now we have 18 electrons total. And you'll notice that this became like argon. So it has the noble gas configuration of argon. It didn't become argon, it just has its same electron setup, but the proton number is still different, so it's not argon, it's just the phosphide ion with additional electrons. Hence why we have a charge of -3 instead of a neutral atom like argon. So this is isoelectronic to argon. We can go ahead and write a complete electron configuration for this. So for the regular neutral phosphorus, I'm going to do 1s2, 2s2, 2p6, 3s2, 3p3. And you'll notice that, so this is regular phosphorus neutral. We want to add electrons to this p here. And we only have room for 3 more. So to do that, we'll get p-3. And that will be 1s2, 2s2, 2p6, 3s2, 3p6. And this is like argon. We added 3 electrons to that valence shell, and now we have 8 valence electrons. So we have a noble gas configuration, isoelectronic to argon. And that was predictable because we had a nonmetal, likely gaining some electrons there. So let's go ahead and take a look at the lead 2+ and the lead 4+. We're going to start off by doing our electron configuration actually first for just the regular lead. Let's just do Pb. We'll do that in red. So Pb will be in red, and then we'll do the other ions in the different colors there. So we'll start with Pb. We'll do its neutral configuration using our periodic table of elements. It's found over here. Lead is way down here. So this is a pretty big configuration that we're dealing with here. It looks like we're going to have to go through some F block elements as well. But basically, we're going to have, so 1s2, then 2s2, then all the way 2p6, then 3s2, then 3p6, then 4s2 here. Then we're going to our 3d10s over here. Then we're going to go into our 4p6. Then we have our 5s2 over here. And then we're going into our 4d10s, and then our 5p6. And now we're going into our 6s2 over here. And then before we go into the D block, we need to go into the F block because we're here, and that means we have to go here. So the F block starts at 4F, so 4F14 all the way through here. And then we have our 5d10s all the way over here. And then finally 1, 2, and that would be our 6p2. So that's a long electron configuration, but that's okay. It's some good practice there. So let's go ahead and write that out. We'll have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We have 3d10. We have 4p6, 5s2, 4d10, 5, so 4d10, 5p6, 6s2. Oh, I'm running out of room there. Then 4f14, let that continue down there. 4f14, 5d10, make a bit more room. 5d10, 4f14, and 6p2. Wow, that was a long one. You know what? Let's write this also just as its noble gas configuration. So lead was xenon, right here, right? So this is xenon. This is in period 1, 2, 3, 4, 5. So xenon's in period 5. So that means 5p6 would be where xenon ends at. So I can replace everything up to 5p6 by xenon. Let's go ahead and do that just to make our lives a bit simpler. Everything up to here by xenon. And so I would get 6s2, 4f14, 5d10, 6p2. So this would be our electron configuration, the shorthand notation for it. Now, I'm going to continue using that. I know it says complete electron configuration, but in the interest of saving some space here, I'm going to use the noble gas configuration, and we're going to make the ions for them. We're going to do the 2 plus and the 4 plus. So what color did we say the 2 plus was? The 2 plus is green. So you'll notice that we need to remove electrons from the outermost valence shell. And we have phosphorus in the p block elements, lead in the p block elements. And so the valence electrons that we're going to be taking from are the S and the P. So we want to remove from the highest P first and then the highest S after. So this is going to be our first removal over here. This is the highest P. So we're going to be removing the 6p2 to make our lead 2 plus. And again, I'm writing a shorthand configuration even though it says complete there. So 6s2, 4f14, 5d10. So we've removed the 6p2 to make the pb2 plus. So that has now formed our pb2 plus. And now from here, we can form the 4 plus. That means we're removing 2 more electrons in addition to what we've already removed. And what color did we say that was? We said that was the orange color. So Pb4 plus is the orange color there. And so we remove next from the highest S. So remember, we always want to go from, if we're in the P blocks, we do P first, then S, and if possible, D, but generally we don't do that. So usually P and then S in the P block, and that's about it. And notice that we can remove the 2s electrons that are located over here, the highest energy S. And that would give us xenon, 4f14, 5d10. And that would be our electron configuration for the 4 plus ion. So you can kind of take it in little steps. I would always do the neutral configuration first. Take a look at what block it's in. So P block, for example, would lose from the P first and then the S. If you're just asking for the 2 plus, do the P. If we're asking for the 4 plus, then remove the remaining S's after. And then now we're nice and stable because notice that we have these full shells below here for 4 plus. But 2 plus is also stable because it has these full, I shouldn't say shells, let's just say subshells. So it has these full subshells as well, which is why 2 plus is a common ion that you'll see for lead, because it has all these full shells here. And then this 4 plus here has these full shells, so that's nice and stable as well. And then you might say, well, why can't you remove, the 14 or the 10 d electrons and then have the full F shell? Well, I mean, theoretically you could, but it takes more and more energy to remove electrons every single time. And so chances are there's just not enough energy available to do that. So the right amount of energy to give you the perfect stability would be really just removing the 2 or removing 4 total. And that would be our complete electron configuration, or our, we cheated here, our noble gas configurations for lead. So let's go ahead and try this out on our energy level diagram over here. And so just based on our electron configuration, I'm just going to start with the the neutral one first. And so that went up all the way to 6p2, I believe. So I'm just going to start filling electrons and make my way all the way to 6p2 because that's what I saw in my configuration. Instead of counting and losing track here, and I know I should be doing singly first, but when you know it's going to fill this many up, I can start doing singly near the end. And that's because I have experience with this. Don't build this habit. In fact, just to make sure you don't build a habit, I'm just going to go singly. And then pair. Almost there. That's a lot of arrows. Very close. Notice we're building up, adding to the lowest energy levels first, and then making our way up higher. So then next we have to add to the 6s2, and then to the 4f, and then fill these out here. And then we have to go to the 5d10, and then lastly, to our 6p, we only had 2 there. There we go. And then I'm just going to circle and remove for each ion based on the color. So for the Pb2 plus, 2 plus, you would have removed, so in green, these 2 for Pb plus 2. And then for the Pb4 plus, you would remove those 2 plus these 2 here for Pb plus 4. And that there is our energy level diagram for Pb, Pb2 plus, and Pb4 plus. Lots of arrows to draw there. So what we saw here is the ion formation for phosphide, and then also for lead 2 plus and lead 4 plus, as well as the regular lead. It was a bit of a longer one, but it's great practice to really put your electron configuration skills to the test. In the next video, we're going to take a look at some anomalous electron configurations, in other words, electron configurations that have some exceptions. But before we get to that, please be sure that you understand all these typical electron configurations that do not have exceptions, as well as the ion configurations, so that the anomalies will make more sense to you.